Hi everyone, in this video, we'll explore transformers, groundbreaking development in the field of language modeling. So transformers extends and enhances the capability of the LSTM and RNN-based language models, which we covered in our last video. So it enables more effective and efficient processing of word input. So transformers are developed to address some of the limitations of the LSTM and RNN, which we highlighted in our last video. So unlike their previous models, transformers process input words in a parallel model rather than a sequential manner. So this removes the recurrence problem, and the mechanism found in a recurrent neural network in LSTM, and it leads to more significant improvement in efficiency, especially in capturing longer sequences. And Transformer introduces a unique features that we will be revisiting and we'll be visiting a little bit more in detail, which is the ability to process words both from left to right and then right to left. So providing a more comprehensive understanding of the context of the words and the sentence. Additionally, the attention mechanism, which we'll be covering today in transformers, allow the models to focus on the specific aspects of the sentence and identify the important words given a specific context so that we can enhance its ability to understand the nuance of the language. And also Transformer utilizes the encoder and decoder architecture, which we'll be also highlighting today in our video. The encoder, in short, processes the input text while the decoder generates the output text. So this structure is versatile, and then it could be stacked and it could be combined in different manners. And so with that, it allows for a wide range of application in language modeling. So we're going to be covering encoder-only models such as BERT, and this model focus on understanding and interpreting the language. So BERT, for instance, is designed to understand the context of a word in a sentence, making it highly effective for tasks like text classification, sentiment analysis, or question answering. On the other hand, decoder-only model, they are designed and tailored for generating text. So GPT that you utilize almost every day will be a decoder model. They take the encoded information and produce a sequence of words useful in applications like language translation or language generation. Lastly, the encoder-decoder model, which combines the first two elements. These models combine the strength of both the encoder and the decoder. So these models are more suitable for tasks that involves both understanding the text and generating language, such as machine translation. To summarize, our transformer model represents a significant advancement or leap forward in natural language processing from the precedent of like the LSTM or RNN model. And then in our next of the video, we're going to be capturing some of the important aspects and attributes of transformer model that makes the transformer models very powerful, and which will be highlighting the attention mechanism and then the encoder-decoder architecture. So let's see. So what's an attention? So William James defined attention in psychology as the taking possession by the mind in clear and vivid form of one of what seems several simultaneously possible objects or trains of thoughts. Focalization, centralization, and concentration of consciousness and of its essence. So this definition emphasizes that humans selectively and directionally identify some of the aspects and the nature of human cognition in order to extend our ability to focus on the specific aspects while ignoring the other when you're providing attention. So it's like driving. You're not necessarily focusing on every single aspect that is happening on the road, but the specific part in general that will help you be able to make the right decisions. But shifting our focus on how this attention is conceptualized in machine learning, specifically in transformer model here, attention isn't about human consciousness, but about how algorithm can actually selectively focus on the certain parts of the data in order to tackle the task more effectively and efficiently. So it involves assigning weights to different elements of the input so that we could highlight the importance of some parts over the other while conveying the task. So while both concepts share the core idea of selectivity, so we select the specific part that we need to provide attention to, there are definitely notable differences. So human attention, as described by William James here, is sequential and constrained by cognitive load. In contrast, attention mechanism in machine learning are not constrained by those cognitive load. So what does it mean by not being constrained by the cognitive load? That will actually mean that machine learning, an attention mechanism in machine learning will enable us to handle multiple elements simultaneously or in a parallel manner. So we'll be able to effectively and efficiently understand and process a lot of things at the same time. So more specifically, the attention mechanism allows transformers to weigh the importance of different words in a sentence so that we can process and understand them better. So unlike the previous model that processes words in a fixed order, transformer uses attention to dynamically determine which part of the sentence are more relevant for understanding a specific words or generate a response. For example, consider this sentence, the cat sat on the mat. A traditional LSTM model might sequentially process each word starting from the to cat sat on the mat. But a transformer model with attention can simultaneously focus on cat and mat, which will be important to process a word set. Understanding that these are the keywords, and so that the attention mechanism understands that these are the keywords that define the action. So this capability is crucial when dealing with longer and even more complex architecture of the sentences where the relevance of each word can depend heavily on a word that is very, very far apart, even a couple sentences apart. So the attention mechanism enables us to model and attend to these distant words so that we can effectively capture their relationship to process the target word, for example, in the sentence, like the word set. And moreover, the attention mechanism is not limited to looking at the words in isolation, so we can actually look at them in a parallel and simultaneous manner. And it understands the context of each word in relation to the entire sentence or even a larger body of corpus or text. So this holistic approach of language processing makes transformer be able to capture something that is much more subtle and more nuanced, and something that is like an expression that we use a lot, so which cannot be really captured just by looking at this simple word. So this actually makes the transformer attention mechanism very versatile, so it can be applicable to across various domains in NLP. So we use attention mechanism in NLP to tasks like translation, summarization, and beyond NLP in image processing, where detection of the specific object or the classification of the images, which require people to understand the global context of the input image. Then let's explore how these attention mechanisms are created or generated and what the integral elements of these attention mechanisms are. So the integral elements or the components of the attention mechanism could be broken down into three different aspects: the query, Q, the key, K, and the value, V vectors. So understanding this vector is very important in understanding how transformer processes information. So we'll delve into the mechanism of this attention functionality focusing on this Q, K, and V vectors, which interact to create a dynamic and the context-aware processes in attention mechanism. So let's take a look at the Q first. The query vector, we can actually thought of it as like a spotlight. So just as a spotlight highlight a specific area on the stage. So the query vector or the Q focuses on the specific or particular element of the input text data or the sentence. So in the context of the language processing or NLP, if the model is examining a specific word, the Q vector actually encapsulates the feature of the word and its role and its meaning and the relation of this word in a sentence. So this vector will act like a question posed to the model and asking for which part of the information is relevant from the rest of the data in order to tackle this task. And moving on to the Q vector, the key vector, and you can imagine a set of a signpost in order to understand key vectors. So each element in your data set, each word in text carries a signpost or a key vector. So these vectors signifies what information in the data set that you need to process that might be relevant to the Q vector or your query. So each key vector or K vector is a potential match to the query that you're asking for. And it also provides a degree of match, which determines the relevance of the information that's associated to your query. And then the last element is a value vector, V, which is very similar to the treasure trove of information or the final information, the target that we're looking for. So each key or the K vector, there's a corresponding value vector containing that information or the content of the key that you're looking for. So if a key is deemed relevant to the query, then the information in its value vector is brought forward. So this is like finding the right key to unlock the treasure chest of the information so that we can give them the specific treasure, which is the value. So in our language example, if the model determines that a particular word represented by the key is crucial for understanding the query, Q, the information in the corresponding value, V, like the words that is specific to the context or usage, or the specific part of the word that is supposed to come after the sentence is utilized in this processing. So the model uses Q vector, the query vector, to prompt the data set, K vector, key vector as an identifier of the potentially relevant information associated with the Q, and then the value vector, which provides the actual content that is utilized based on this relevance. So this dynamic interplay allows a transformer to process information in a very nuanced and context-aware manner. So we can enable it to handle complex tasks that are really depending on a remarkable longer sequences or longer dependencies. So mapping this element into attention function is actually conducted in 3 phases. We'll namely call it a scoring in the first phase. So the first step in the attention function, we call it a scoring phase, is the calculation of a score of the Q query and the key K match. So Q and query and the key pair match. So the score is computed as a dot product between the query and the key vector. So it measures the relevance of each key to the query. So the higher score will indicate that there is a greater relevance of this key according to this Q. And after the scoring is done, then we'll typically do the normalization using a softmax function. And this normalization converts the score into a probability distribution. So it will ensure that the weights sum up to 1. And these normalized scores represent the weights the model assigns to each value vector. Next, the model performs a weighted sum of all the value vector using the calculated weights. And this means that each value vector is scaled based on its corresponding weight, and that all scale values are summed up. The output of this sum of this final output of attention the output of the sum is the final output for the attention function for the specific query that we ask for the Q. So this process allows the model to focus on the most relevant information for each part of the input. For example, in a sentence, the model can dynamically focus on the words or the phrases that provides the most context for understanding or generating a specific word. Now let's take a look at the practical example of how attention and transformer models can be visualized. And hopefully this will be able to help you sort of visualize what's happening with this Q, query, key, and then the value vector. So we can actually visualize the transformer architecture using a tool or a package like BERT 2017. So this visualization shows us that the inner working of the transformer model as it processes a sample sentence. And you can see that on the left, we have a sample sentence called, I went to the store, and at the store, I bought fresh strawberries. And you can see there are the separator and insert and the end of the sentence, but there is a specific token that we are processing using the query Q, and then the key vector, and then the value vector. So let's take a look at this visualization a little bit more in detail. So on the left, we see that the query matrix. In the middle, we have a key matrix. And on the right, we have the combination of the attention score, the query, and then the key matrix multiplied together. And then we applied the softmax function in order to actually represent this in a probability. So each row in the query and the key actually corresponds to the token from the input text. And then the input text token, like I mentioned before, we have all the way from I went to store. At the store, I bought fresh strawberries. The CLS token actually stands for the classification and is used by the models such as BERT, which we'll be covering a little bit more in detail, to aggregate sentence level representation. And SEP actually represents a separator token, making the end of the sentence or a segment. So the attention scores are calculated by taking the dot product of the Q and the key matrix. So you can see the attention scores provided over here, which is then visualized as element-wise in the third panel on the left. So this representation actually provides how each word attends to each other words in the sentence. And so these raw scores are then normalized using softmax function to ensure that they're summing up to 1, forming a probability distribution. So in this particular example, I highlighted the path from the separator token in the query matrix to the key matrix here, and then showing the attention pattern of this specific token. So it is pretty evident that the certain words in the sentence receive more attention as indicated by a darker shade in the key matrix, like a darker shade in the key matrix. And after normalization, this pattern becomes even more clear in the softmax function. So you can see the darker shade in the function. So by studying this pattern, we can give insights into what the model seems to understand or deems as important when processing a given word. For example, the SEP token here, SCP, often used to understand the entire sentence, shows significant attention to tokens that might be key to understanding the sentence's meaning. So, yeah. And next, so we'll visit, and then the next, we'll visit the core architecture, another core architectural component of the transformer model, which is the encoder and then the decoder stack. So let's understand how they could actually function and interact to process and generate language. So transformer models use encoder stacks to model the input, and transformer models also use decoder stacks to model the output. So in our previous slide, we provided the examples of what the encoder model, what the commonly used encoder-only model looks like, what a commonly used decoder-only model looks like, and then what are the combination of the encoder-decoder model. So let's begin with the encoder. So encoder is a component that takes raw input data, so the text, to process. So the objective of this encoder model is to understand and encode the input into a higher level and then more of a dense representation. We usually call this an embedding. So in a language task, for example, the encoder transforms a sentence from a source language into some type of embedded form and then capture the meaning of the contextual nuance. So what you're seeing on the right side will be an example of the one encoder model. Here. And then the encoder role is very important because it breaks down the input into the form that the neural network can be able to understand and analyze and utilize. So this involves complex processes where the input is passed through several different layers of the network, and each extracting and condensing information into a further layer. And within each layer of the encoder stack, we can see the input sequence undergoes several different transformations. So it passes through the neural network layer, includes the self-attention mechanism and P4 neural network. And the self-attention layer allows each token to interact with each other, like we have explained in our previous slide. So the self-attention layer essentially makes this model effectively enable the model to understand the entire sequence, not necessarily having to process this from the left to right or the right to left. Now, once the input is encoded, it's time to do the decoding, so the decoder will be the next stage. So the decoder, very similar to what encoding is, decoder takes the embedding from the encoder architecture and begin the task of generating the output in a meaningful format that follows the encoding structure. So the decoder is essentially the reverse of the encoder, if you want it in a more simplistic way, and it decodes the abstract representation that we learned in a more understandable output, such as generating a text. For example, in machine translation, the decoder will decode the encoded output from the English sentence and then provide it to a equivalent French sentence. So here I have an example of a stacked encoder in an encoder and then the stacked decoder in the decoder only model. So the decoder essentially reveals the information step by step, transforming the abstract information it learned from the encoding output into a structured sequence, and it ensures that the final output is maintained with the integrity and then following the very similar structure of the original input. So in summary, encoder and decoder are like the two sides of the same coin, the neural network. They work together in harmony to transform input data into meaningful output and supporting the complex tasks like translation, summarization, and even image captioning when you're dealing with the image as an input. And in this illustration, we'll showcase how some of the practical example of this encoder-decoder architecture in various tasks like machine translation. So our input is a French sentence of Je suis étudiant, which translates to I'm a student in English. So this sentence enters a model where it processes by a stack of encoder, and each encoder layer works to encode the sentence into a higher level, higher dimensional space, while it's capturing the sentence semantics, grammar, or the context or the contextuality of the sentence. And then from the final encoder layer, the encoder representation is passed through the decoder stack. And in the decoder is trying to do the job to take this abstract representation from the encoder to create a equivalent sentence in the target language, for example, in this case, in English. So each layer in the decoder stack actually contributes to the generation of the target sentence, I am a student. Starting with the initial encoded information, the decoder begins to construct the English translation word by word. So it uses the context provided by the encoder to ensure that each word it selects is appropriate for the translation task. So the output of the decoder stack is a translated sentence like I explained here, I'm a student, and this output demonstrates that the model was able to understand the contextuality and then be able to create it in an understandable format in English. Then what are some of the existing transformer models? And then how can we actually train them and use them? And some of the prominent transformer models includes BERT, bidirectional encoder representation from transformer, which is designed to understand the context of words in a search queries. And GPT is something that is widely used, which represents generated pre-trained transformers known for its text generation capabilities. And there are also other type of transformer models, such as T5, text-to-text transformer, a transfer transformer, which frames all NLP tasks as a text-to-text problem. And training these models often takes like a semi-supervised or an unsupervised learning, and it involves using like a large corpus of the text data, which may be partially labeled or entirely labeled. So we can map them to a semi-supervised or unsupervised manner. And the model learns to predict parts of the text and fill in the blank or even translate the text based on which transformer model that we look into in order to process this vast amount of information that we're learning from the text.